So I'm going to just briefly summarize a new technology called structure from motion that many geologists and geomorphologists use in their research to understand the landscape. And the structure from motion is a form of digital photogrammetry, and I've applied this form of digital photogrammetry into the classroom. I'm from the geology department. And I just want to summarize that I applied this to a course in Geology 143, and it's a course called Active Tectonics, where we actually go out into the field and we study the landscape. And what we did was we brought a drone out and we flew the landscape. We flew the surface of Earth, and we just took overlapping photos of the surface of Earth. And the students were able to do this. They went out and they mapped what they were doing, and they flew the drone. And I just want to emphasize that some of the learning objectives that we were able to accomplish by using technology in the classroom. And it's just basically, we use methods of science and knowledge to derive some of the current scientific inquiries and questions to explain the existing data. They were able to recognize methods of science in which they were using quantitative and analytical applications to learn different techniques. And basically, we were able to apply this technique, and we were able to see how it influenced society, because what they're studying helps society better understand earthquakes. And just the students in the class here. And so we applied this to two areas, and we're going to demo both areas for you. One is just the picnic area next to the Associated Student Union building, so that you guys can see how awesome this technique is. And then the second method is we went out into the field in the Sierra Nevada mountains. We went camping for 3 days, and while we were camping, we would hike and map the surface of Earth while we were flying the drone to collect all the photos so that we can collect all our data of the surface. Okay. And in general, the technique is very simple. What it is you just take many different photos of an object of interest. And that can be the surface, that can be a human body, it can be a picnic table. And it's important that you take overlapping photos. The photos with high resolution, you need 80% overlap. And there's basically, the photographs are taken from different angles so that the software, it allows the reconstruction of a scene. And the aerial photos will depend on scale, so you can apply a drone, you can actually put a camera on a kite or a balloon, as long as you have these overlapping photos. And this is just giving you an idea of the drone. So you can just imagine the drone moving from one area to the next. And as the drone is taking a photo of the scene, the red dots that you see are known locations of that scene taken multiple times, so that the software can use a method called line of sight imaging to reconstruct the image in 3D. So what we're doing is taking photos, and we're reconstructing a surface of Earth or an image that has an X, Y, and Z that you can then take into a software called ArcMap that is geo-referenced, and you can view it in its overall scale of Earth and of the entire landscape. The processing is very simple. You just import all the photos into a software called Agisoft, and all the students did this in the classroom. The photos realign themselves in the classroom to detect these tie points, those red dots that you saw on the previous slide. And it builds something called a dense cloud. And that dense cloud then allows you to scale and rotate your image in real space. And they first showed how this can be done with the Colosseum. These are just different photos, hundreds of different photos people posted online, taken throughout the years, and they were able to then take that and reconstruct a 3D image of the Colosseum to actually fix it. and repair it. Okay, and they've done it with the White House. Okay, and so now I thought, since I'm the instructor, I'm supposed to know what I'm doing. So I thought I'd have my student, Kerry, he took the class this last semester where we applied this, and he's actually going to walk you through the entire process. And if we have time, we can even fly the drone across this room and reconstruct a 3D image of this room in real time. So we'll try that if we have time. But it was really great for the students to be able to do this technology in the classroom.
So like Kim said, what we do is when we fly the drone, we're taking roughly anywhere from 100 to 300 photos, over 80% overlapping photos of a given area. And so what those photos look like, exported into Agisoft Photoscan, once you do that, is something like this on your right-hand side here. And so from those photos, just to show you, and this is going to be of the associated student building over near the picnic and barbecue area near Duncan Hall. And so let me just show you, oops. So let me go into the next one of what that looks like. So there's an image of the picnic area. And so next what I would want to do is I'd want to align all the photos and create something called a point cloud, kind of what Kim does. And what that does is it creates a bunch of tie points. And basically what tie points are is it is a sparse three-dimensional image of what you're seeing. And so once I create those tie points, it looks something like this. And like I said, it's a very sparse three-dimensional representation of the area. So once we have those tie points aligned, what we want to do is we want to build a dense cloud and fill in the missing images and fill in the missing data. And so once we build a dense cloud, a dense cloud would look something like this. And this isn't the quad, but this is of the glacial moraine that we shot out in the eastern Sierra. And so this is a reconstruction of tie points that were used to align photos, and then basically filled in the missing gaps with this. And so as you can see on here, I can rotate it any which way I want. So basically what we can do with this image, and this is an actual geologic structure, is basically we're looking at fault scarps on this image, and they're very, very subtle. And for a trained geologist, they're not so subtle. And so from this, what we can do is we can draw polygons and then export this into ArcMap and basically measured the displacement, the vertical displacement that this earthquake fault has caused. If we want to, we can sample material above and below the fault and take that with the measured displacement to get an average slip rate. And so that's how we used it in the class. We used that to we already had the dates, so we went out and we measured the vertical displacement, and we were able to calculate a slip rate on these two faults in the eastern Sierra. So anyway, that's how we're implementing into the classroom, and we hope to use this technology in her advanced active tectonics class. And I know some of her grad students are using this as well in their own master's thesis projects. So we're very pleased with the results we've gotten so far, and hopefully we will continue implementing this technology, and as it grows, we will adapt with it as well. So.
Well, do you guys have any questions? Oh, yes. This is a Phantom. This is off the shelf. Mm-hmm. No.
And also, what camera are you using?
I think this comes with the Phantom. So you don't. There's no choice. It's connected. Okay. You use what's really cool is you can use any smartphone or an iPad. It's through Bluetooth, and so you view all the pictures that you're taking, or that the drone is taking, basically on your phone. You just download an app.
Okay, great.
Yeah, and the GoPros, they work pretty well too because they have dive stabilizers, but the Phantom has a GPS on it, so you don't have to worry about georeferencing and fish eye effects.
We have a 3DR drone also.
Yeah, we have another drone that that goes with the GoPro.
the geography department is shopping for a drone. So
Oh, so come talk to me. I know all about drones
Okay.
right now. Yes.
good.
Yes.
Are you going to make the room 3D?
Oh, should we try it? Do you guys want to? It'll take a little bit of processing. We can do a.
I would recommend not doing it just because we have to acquire satellites, and then if something were to happen in here, I wouldn't want to be responsible for breaking the drone. Usually when we fly it, I don't think you're allowed to actually fly them on campus due to FAA regulations that we've had to seamlessly.
Only above a certain height.
Yeah. So.
I've looked into it. That's okay. Follow the law. Okay. Yeah.
I have a question around the, so when you were maneuvering the image there, you had a 3D image that you'd actually managed to construct based
Yeah.
on all the photographs you'd taken, and you were rotating it through 360 and in multiple directions.
Yeah.
There you go. So is that actually happening on the PC itself, or
Yeah.
is it? So this is actually happening on your PC,
Yeah. This is on the computer.
and that's already pre-built, or is it?
That's so basically the photos are taken and you get a 3D image of the photos of 2D to 3D.
And how long does it take to actually, if you had 300 pictures and you were trying to, something, whatever you want, but
So the time it takes to reconstruct a three-dimensional image is directly proportional to one, how many pictures you have, and then the quality at which you want to reconstruct that. You can do it
that's why
on
I
low
was
quality.
asking. So can you give me some examples?
Sure. If it's something with 300 pictures, I think this one was right around 200. And I think this took on high quality, it took us about 2 to 3 hours to reconstruct the image.
That's all?
To match the data points. Yeah, luckily she was able to acquire a very high-end gaming computer with a really great graphics processor on it, and so and lots of RAM and lots of memory. And so, if I was running it on this PC, you could probably expect to almost double that time.
Right,
but with more computing power.
It's still pretty slick. So the matching up, the conversion from 2D images to 3D construct, is that automated? You don't have to do anything. You just say, here's all my pictures, identify the points on the pictures, and work it out for me. Thank you very much. Have a nice day.
Yeah, absolutely. Yeah, it's that easy. Yeah,
Wow.
everything is in the software. We just basically, we go into workflow here, and we'll align all the photos. And then once the photos are aligned, that takes about an hour. So if it's on high quality, then we will build the dense cloud once it's made all those tie points, and then so it can fill in the missing
And
data.
it's true 3D. As you're rotating that, it looks like it's true 3D.
Show the image of the photos. Can you?
Yeah.
I think you have to close. I think maybe you can't have both of them on. So we're going to try to show you an image where you can actually see where all the photos were taken, and then you can see the location of the tie points.
Let's see if I can get it to work here.
Okay, so those are the tie points. Okay, so now it's just done the 3D reconstruction of the quad. I don't know if you guys are familiar with this area. It's on campus. It's by the student union. What is that?
It's the associate student building
Associate student building.
out next to Duncan Hall.
So that's the 3D visualization of, and the 3D construct of Duncan Hall. And this is in low resolution. And then want to show them the photos.
So I can show you where we took the
Yeah,
photos from also.
yeah. And so now you can see where all the photos were taken to reconstruct that image. And so those photos were just imported into this program, and the output is that reconstruction.